So we noticed that we have this invariant quantity d tau squared, and when we divide by d tau squared, of course, we get 1. And so the right-hand side looks like this. And we noticed already that we could write this as two vectors, right? A row vector and a column vector being multiplied by each other, where this one has a minus sign in it, and this one doesn't. So we just have dx bar by d tau. And that, of course, gives us the same thing back. Gives us this quantity here, dt bar over d tau squared minus dx bar over d tau squared, where we just squared the entire ratio instead of squaring the numerator and the denominator. But of course, we know that we can write this invariant quantity, this quantity that's equal to 1, as a row vector, dt by d tau, without a minus sign, and have the minus sign come in as a result of the operation between this row vector and a matrix, right, which we called the metric, and then have our column vector, dt bar by d tau, dx bar by d tau, like that. So this suggests that we define a quantity that we can call a 2-vector, because this is like a vector with components, and it has 2 components, so it's a 2-vector. And this is sort of the special case of a 4-vector, because our space-time is 2-dimensional, 1 space dimension and 1 time dimension, not 3 space dimensions and 1 time dimension. So this is sort of a special case of a 4-vector. And we define this quantity as a 2-vector with a symbol that indicates that it's a kind of vector with components dt bar by d tau and dx bar by d tau. It's not immediately obvious why we use v. V suggests components of velocity, and we will try to turn this into something that here we'll have something that's straightforwardly a velocity component. So we'll make this more straightforward in recognizing that it's a velocity 2-vector. But what we want to recognize here is that this kind of 2-vector is needed to get a constant or an invariant through this metric object. So in other words, we can write what we've just done above as 1 is equal to a VA, right? So that's an object like this times an object like that, where this represents this object. And then we have an object like that, which represents this object. And so when we do the operation, when we do this operation, this with this, we get a kind of 2, we get a 2-vector from that. So this operation gives us a 2-vector that's a little bit different from this one, right? Because it's the one with the minus sign. Right here it is. So we lower the index to indicate that difference, to indicate that the metric has sort of operated on it, has influenced it. And so we end up with an object that's similar to the other one, but with a different index. We lower the index, and this just means that we're doing the component of one times the component of the other, and we sum. Okay, so the repeated index means that we sum, we do 0, 0, and then we do 1, 1. And of course, in 4 dimensions of space-time, we have 0, 0, 1, 1, 2, 2, and 3, 3. That's assuming that we have a special kind of metric like this, where the off-diagonal terms are 0. Otherwise, we would have cross terms like 0, 1, or 2, 1, and so on. So basically what we are arguing here, we're motivating the idea that the metric takes us from this object without the minus sign to the object with the minus sign. Or we can go the other way. We can have an object with a minus sign with a lower index and go to the other object the other way. So we could think of this lowered object, this object with this 2-vector with a lower index, as the operation as a result of this operation on this kind of vector here, where we operate with the metric. And again, we have to repeat indices, and actually I made a mistake here. I use C and B, so I want this to be B. So this would be G. So if the V0, right, so if we think of a 2-vector with 2 components, a 0th component and a 1 component, then the 0th component has a G00 V1 plus G11 V1. And the other way around, right, we get by operating with we'll have to look at this a little bit more closely, but notice that the indices here are up. So this metric that takes us, this object, which can be written in matrix form, that takes us from a lowered object to an upper 2-vector, has indices that look like that, and we do the same summation convention. But this is going to be very similar to that kind of object. So we've motivated the existence of 2 vectors, which are specific, in this case, to our 2-dimensional space. More generally, it's 4 vectors that come from the notion of invariant quantities. So the invariant quantities are associated with 2 vectors, or more generally, 4 vectors. And so we're going to build 4 vectors and look at the invariant quantity associated with these 4 vectors.